Welcome to the session. Now we are going to see about static and dynamic characteristics of transducers. I am P. Sindil Kumar, Assistant Professor, Department of Electronics and Instrumentation Engineering, Erode Sengundar Engineering College, Perundurai. Static and dynamic characteristics of transducer. The performance characteristics of a transducer or instruments are mainly divided into two categories: static characteristics, second one is dynamic characteristics. Some, some applications involve the measurement of quantities that are either constant or very slowly vary with time. Under these circumstances, it is possible to define a set of criteria that gives a meaningful description of quality of measurement without interfering with the dynamic description that involve the use of differential equations. These criteria are called static characteristics. Normally, static characteristics of a measurement system are, in general, those that must be considered when the system or the instrument is used to measure a condition not varying with time. However, many measurements are concerned with rapidly varying quantities, and therefore, for such cases, we must examine the dynamic relation which exists between the output and the input. This is normally done with the help of differential equations. Performance criteria based upon dynamic relations constitute the dynamic characteristics. The various static characteristics are accuracy, precision, sensitivity, linearity, reproducibility, repeatability, resolution, threshold, drift, stability, tolerance, range or span. These are all the various static characteristics of transducer. The first one is accuracy. It is the degree of closeness with which the reading approaches the true value of the quantity to be measured. So we have a new term is called true value. So what is true value? The true value of quantity to be measured may be defined as the average of an infinite number of measured values when the average deviation due to the various contributing factors tends to zero. Such ideal situation is impossible to realize in practice, and hence it is not possible to determine the true value of a quantity by experimental means. The reason for this is that the positive deviation from the true value does not equal the negative deviation and hence do not cancel each other. Thus, normally an experimenter would never know that the value or quantity being measured by experimental means is the true value of the quantity or not. So, in practice, the term true value is refers to a value that would be obtained if the quantity under consideration were measured by exemplar method. That is the method agreed upon by experts as being sufficiently accurate for the purpose to which the data will ultimately be put to use. So from that we can conclude it is very difficult to find out the true value by practical method because we need to take a infinite number of readings and it is impossible, so we are going for a standard method, so that is exemplar method. It is agreed by the expert and a sufficient amount of readings were taken and further it is processed. So this is at the end we can get the true value. The accuracy can be expressed in following ways. Point accuracy. Such accuracy is specified at only one particular point of scale. It does not give any information about the accuracy at any point, any other point on the scale. It is only at particular point of scale. Next one, accuracy as percentage of scale span. When an instrument is uniform scale, its accuracy may be expressed in terms of scale range. The third one, accuracy as percentage of true value. The best way to conceive the idea of accuracy is to specify it is in terms of the true value of the quantity being measured. Precision. It is a measure of reproducibility. That is, given a fixed value of a quantity, precision is a measure of degree of agreement within a group of measurement. The term precise means clearly or sharply defined. As an example of the difference in meaning of the two terms accuracy and precision. For example, we have an ammeter which possesses high degree of precision by virtue of its clarity, legible, finely divided, distinct scale and neat edge of pointer with mirror arrangement to remove parallax. Let us say that its readings can be taken to 1 by 100 of an ampere. At the same time, its zero adjustment is wrong. Now, every time we take a reading, the ammeter is as precise as ever. We can take readings down to 1 by 100 of an ammeter, and the readings are consistent and clearly defined. However, the readings taken with this ammeter are not accurate because they do not conform to truth on the account of its faulty zero adjustment. The precision is composed of two characteristics, conformity and number of significant figures. Conformity. Consider a resistor having true value as 23,85,692 ohms, which is being measured by an ohmmeter, but the reader can read consistently a value as 2.4 young. Due to the non-availability of proper scale, the error created due to the limitation of the scale reading is a precision error. Number of significant figures. The precision of a measurement is obtained from the number of significant figures in which the readings is expressed. The significant figures convey the actual information about magnitude and the measurement precision of the quantity. The precision can be mathematically expressed as P is equal to 1 minus x bar divided by xn bar. P is precision, xn is the value of nth measurement, xn is the average value, the set of measurement values. Sensitivity. Sensitivity denotes the smallest change in the measured variable to which the instrument responds. It is defined as the ratio of the changes in the output of an instrument to a change in the value of the quantity to be measured. Linearity. It is normally desirable that the output reading of an instrument is linearly proportional to the quantity being measured. An instrument is considered if the relationship between the output and input can be fitted in a line. One of the best characteristics of an instrument or a measuring system or the transducer is considered to be linearity. That is, the output is linearly proportional to its input. Most of the systems require a linear behavior as it is desirable. This is because the conversion from a scale reading to the corresponding measured value of input quantity is most convenient if one merely has a multiply by a fixed constant rather than consult a nonlinear calibration curve or compute from nonlinear calibration equations. Also, when the instrument is a part of large data or control system, linear behavior of the part often simplifies the design and analysis of entire system. Therefore, relationships to the degree of straight line relationships are common. That is, linearity is common. For an instrument, calibration curve is not a straight line. It should not be concluded that the instrument is inaccurate. We can't say this is a misconception. A nonlinear behavior does not essentially lead to inaccuracy. Such an instrument may be highly accurate as ever. However, most of the time it is necessary that the measurement system component should have linear characteristics. For example, the resistance used in a potentiometer should vary linearly with displacement of sliding contact in order that the displacement is directly proportional to the sliding contact voltage. Reproducibility. It is the degree of closeness with which a given value may be repeatedly measured. It is specified in terms of scale reading over a given period of time. Reproducibility and repeatability are a measure of closeness with which a given input may be measured over and over again. The two terms cause confusion. Therefore, a distinction is made between the two terms. Reproducibility is specified in terms of scale readings over a given period of time. On the other hand, repeatability is defined as the variation of scale reading and is random in nature. Span drift or sensitivity drift. If, if there is proportional change in the indication all along the upward scale, the drift is called span drift or sensitivity drift. So it starts with 0 but does not follow the linear one. So it will follow the different path. So the first graph represents the span drift. Next one is zonal drift. In the case of drift occurs only a portion of span of an instrument is called zonal drift. Resolution. If the input is slowly increased from some arbitrary input value, it will again be found that output does not change at all until a certain increment is exceeded. This increment is called resolution. Next is threshold. If the instrument input is increased very gradually from 0, there will be some minimum value below which no output change can be detected. This minimum value defines the threshold of the instrument. Stability. It is the ability of an instrument to retain its performance throughout its specified operating life is called stability. Tolerance. The maximum allowable error in the measurement is specified in terms of some value which is called tolerance. The minimum and maximum values of a quantity for which an instrument or transducer is designed to measure is called range or span. Dynamic characteristics. The set of criteria defined for the instrument or transducer which are changes rapidly with time, is called dynamic characteristics. The various dynamic characteristics are speed of response, measuring lag, fidelity, and dynamic error. Let us see the dynamic characters one by one. Sensitivity. Sensitivity denotes the smallest change in the measured variable to which the instrument responds. It is defined as the ratio of the changes in the output of an instrument to a change in the value of the quantity to be measured. Linearity. It is normally desirable that the output reading of an instrument is linearly proportional to the quantity being measured. An instrument is considered if retardation type. In this case, the response of a measurement system begins immediately after the change in measured quantity has occurred. Second one, time delay lag. In this case, the response of the measurement system begins after a dead time after the application of the input. Resolution. If the input is slowly increased from some arbitrary input value, it will again be found that output does not change at all until a certain increment is exceeded. This increment is called resolution. Next is threshold. If the instrument input is increased very gradually from 0, there will be some minimum value below which no output change can be detected. This minimum value defines the threshold. Span drift or sensitivity drift. If, if there is proportional change in the indication all along the upward scale, the drift is called span drift or sensitivity drift. So it starts with 0 but does not follow the linear one. So it will follow the different path. So the first graph represents the span drift. Next one is zonal drift. In the case of drift occurs only a portion of span. Peak overshoot. It is the maximum value minus the steady state value, normally expressed in terms of percentage. Settling time. It is the time taken to attain the response within plus or minus 2% of steady state value. Rise time. It is the time required for the response to rise from 10% to 90% of its final value is called rise time. That's all about the static and dynamic characteristics of a transducer or a measuring system. Thank you.